Okay, I guess we'll get started again. So the situation we're considering is a symmetric top spinning on its tip here. We've introduced two coordinate systems. We've introduced a prime system which is fixed in space, corresponding to a stationary observer, for instance. We've also introduced this XYZ coordinate system which is attached to the top. And if it's attached to the top, it means it should be rotating. So we have two coordinate systems with coinciding origos, and one is rotating with respect to the other. And this is exactly the type of scenario we've been considering so far. So just as for the wheel, due to the symmetry of this body, we can perhaps have an intuition about what kind of coordinate system that will give a diagonal matrix of inertia. It is precisely the coordinate system we have chosen, incidentally, with the z-axis along the line just going through the middle of the top. So in the unprimed coordinate system, the matrix of inertia is diagonal, and you can show this mathematically if you want. So similarly to our squished Earth that we considered a couple of lectures ago, we have a situation where two of the main moments of inertia are the same, whereas the third is different. Now, this coordinate system is very practical to work in, as we know, because the kinetic energy and also the angular momentum take a very simple form. Using some convention, it looks like that. So that's the kinetic energy. And we see that it depends on the moments of inertia, but it also depends on the angular velocity vector components. So having now introduced these three Euler angles, which describe the rotation of the body, the question is, how does the angular velocity vector relate to these angles? And this is also something that we have considered previously, namely expressing the angular velocity vector omega in the rotating coordinate system through these Euler angles. And by doing so, we get this. And this, you may consult your notes, is something we derived a couple of lectures ago. So these are the components of the angular velocity vector as seen in the rotating system, expressed through the Euler angles. So what enters the expression for the kinetic energy is the sum of the squares of omega 1 and omega 2. And using this, we obtain the following, due to some cancellation of terms here. Omega 3, unfortunately, we can't do very much about. It's already pretty much as simple as it gets. So it looks like this. So by inserting these expressions for omega, we have the following kinetic energy. Now, I'm also going to write up the potential energy, and by then you may have identified where I'm going with this. I would like to write down the Lagrangian of the system. So this example is meant to show you how you can also use this Lagrangian method to analyze rotational motion and obtain equations of motion that describe it. In general, if we divide this top into small subregions, we can write the kinetic energy as follows, where each subregion has mass mi. But what we'll find out if we perform this summation is the well-known result that gravity acts effectively on the center of mass as if all the mass was gathered in it. So we get this, where large r is now the position to the center of mass. And it's given by, it has a magnitude L, as shown there. So we find that the potential energy is mgl cosine of theta. So the smaller theta is, the larger the potential energy is. And so if the top is turned down on the table, it has zero potential energy. All right, we then have our two necessary ingredients for a Lagrange function because we're dealing with a conservative system. We only have gravity acting. So let's take a step back and consider what we have to work with. This is our starting point. We have three generalized coordinates, theta, phi, and psi. And so we should expect to obtain three Lagrange equations, one for each generalized coordinate, as we know. And each equation is a second-order differential equation. And all of these equations depend on each other since you have all the coordinates mixed in the equations in general. So that seems like a pretty formidable task to solve analytically. But as we hopefully know by now, the first thing to do once you've obtained your Lagrangian is to any ideas? What's the first thing you do when you have your Lagrangian? It's one of the most important messages in this course. I sincerely hope you know it, or I have failed greatly.
Write down the equations of motion and conjugates momentum.
Mm-hmm. that's one way to do it. Definitely, you can write down the equations of motions, but there's one thing which is actually very beneficial to do first, before that. Yep.
Identify cyclic coordinates.
Yes. Cyclic coordinates or symmetries and conservation laws. So let me repeat that. That's really the take-home message. Symmetries and conservation laws. The first thing you do when you have a Lagrangian is to look for symmetries, because we know that symmetries can always reduce, or should be able to reduce, the difficulty of the problem. And as you say, this is equivalent to looking for cyclic coordinates to begin with, at least. And it's also related to what you said about the canonical momentum. Because we know that there's a relation between if a coordinate is cyclic in the Lagrangian and its canonical momentum. Okay, so let's look for cyclic coordinates or symmetries, meaning is there some variable here we can change without changing the Lagrangian? That's a symmetry, right? Performing an operation or something without changing the actual object. Well, I can see at least two cyclic coordinates. Which are they?
Psi and phi.
Yep, psi and phi. The Lagrangian depends on theta, but it's independent on psi and phi. It only depends on the time derivatives of phi and psi. And if these are cyclic coordinates, then the associated conjugated or canonical momenta are preserved quantities. So p phi and p psi, defined by the partial derivative of Lagrangian with respect to the time derivative of the belonging coordinate, are time constants. So let's have a look. The partial derivative of the Lagrangian with respect to phi dot is given by this, and it should be a constant. So we define this constant as I1 multiplied with b. I could just as well have called it b, but we'll see that it's more convenient to name it I1b. But this is not essential. All right, now on to p psi. Which I then similarly name I1a, where a is some constant. Okay, so that's to conserved quantities originating from a symmetry that the Lagrangian has. Do we have any other symmetries, conserved quantities? The energy. The Lagrangian has no explicit time dependence, and hence energy is conserved. So this combination of the quantities in the system should also be a constant. And note that omega 3 is a constant in this problem, since peep psi is a constant and it's proportional to omega 3. So I've just written the energy here in terms of omega 3. Okay, so we have 3 conserved quantities. And let's now see if we can use these equations to simplify our problem. Well, one thing we can do is that we can isolate psi dot from the canonical momentum. So we have this from the equation for peep psi. And let me now insert this equation into the conservation law for p phi. Like this. And we see that by doing so, we are now in a position where we can isolate also phi dot. So we've managed to express phi dot solely in terms of theta. And we can then take this back into our expression here, so that psi dot is also expressed solely as a function of theta. This means that we've been able to now express both of these 3 quantities here, or they're just 2 quantities, phi dot and psi dot, solely in terms of theta. And we know that there is no dependence on phi or psi. So now you might be considering where we're going with this. If I now insert my expression for phi dot and psi dot into the energy, I obtain this equation. And I could just as well have substituted them into the Lagrangian, but the main conclusion is the same. We've managed to reduce the problem to an effective one-dimensional problem. There's only a dependence now on one generalized coordinates, theta. So from having three coupled second-order differential equation, we now have one independent second-order differential equation. And that's really a simplification of the problem. And we were able to do so by first considering the symmetries and conservation laws in the system, and then substituting the associated canonical momenta. So this conservation of energy we can also view as an equation of motion, right? Because this is a differential equation in time. We can do one more simplification with this energy. We see we have a constant term here. And a constant term corresponds to a shift in the potential reference level. So we can just skip this. Redefining our potential minimum level. So the effective problem we are left with we have an effective one-dimensional problem, and this essentially looks like, if you substitute theta with x, this looks like a conventional kinetic energy term, just a particle moving in one dimension, right? This would be 1/2 mass multiplied with velocity squared, moving in some effective potential that depends on x or theta in this case. And you may recall that this is actually not the first time we've managed to obtain an effective one-dimensional description of a higher dimensional problem. We obtained the same thing in the context of central forces, where we were able to use the conservation of angular momentum to eliminate the theta coordinate and just obtain an effective radial dependence. So I hope this again underlines the importance of considering the symmetries of the Lagrangian, because this makes all the difference. Imagine you're sitting at your exam and you have three coupled second-order differential equations. You have either that or you have one second-order differential equation. That makes a pretty big difference. So this is the effective description of our problem. So we should try to solve this now for theta, try to find how theta behaves in order to characterize the motion of this top. Now, we see that this potential depends essentially on cosine theta, because sine squared theta can be expressed as 1 minus cosine squared theta. So it might make life a little bit easier by introducing this variable here, and also defining this constant alpha, just for convenience. And one more constant. We can then write the total energy of the system in the following way. So theta dot squared is equal to u dot squared over 1 minus u squared by using this definition. And here I just substitute cosine theta is equal to u. Now I can rewrite this equation in this way. So what I've done here is to isolate u dot squared and express it through these other constants. So the energy is now contained in alpha. So we have a polynomial here to third order in u, and I'm defining this entire function here as a function of u. So we have an equation u dot squared is equal to some function of u. Okay. So now we have a more or less compact mathematical expression, and we have to try to think about what can this tell us about the motion of the top. We have this relation between the time derivative of theta and the time derivative of u. So we see that if u dot changes sign, it should correspond to sign change also in theta dot, the derivative of theta. So it should correspond to an angle where this velocity changes sign. So the roots of the function f of u should provide us with the angles theta, which are related to u, where this velocity changes sign. And what that means is that, well, the velocity of theta is associated with how the top is oriented compared to the z prime axis. So if it changes sign, it means that it perhaps first is going down and then going up again. So one thing that could be useful is then to try to identify these roots of f of u. And to get a feeling for how f of u looks like, we can consider some limiting cases. Well, one limit is when u goes to plus minus infinity. Then f of u also goes to plus minus infinity. And how can we see this? Well, for large u, this third order term should dominate. And beta is a positive quantity. And so, depending on the sign of u, it goes to either plus or minus infinity. For reasons I will explain in just a little while, it's also convenient to consider what happens with f in the limits plus minus 1. And if you insert plus minus 1 for u in this function, you will get this, which is smaller than 0. It's a negative number. So why have we considered plus minus 1? Why is that interesting? Well, u is given by cosine of theta, and cosine of theta varies between 1 and minus 1, as long as theta is real, which it should be in this case. So one can think of this as the value of f in the extremal points of theta. So let's see if we can try to qualitatively sketch this function now. And I propose to you that it should look something like this. First, we can note that it satisfies the correct limiting values when u goes to plus minus infinity. It has to diverge here and here, but to opposite signs. And both at u equals plus minus 1, it has to be negative. And u is a polynomial to the third degree, so it should have 3 roots. 3 values of u in general, where the value of the function is 0. And so 2 of these values should be here, inside the regime u equals plus minus 1. So we know that one root has to be outside for the following reason. When u goes to infinity, f of u is positive. But at f plus minus 1, f is negative. So somewhere along this line, there has to be a sign change. So one root is outside here. The two others are inside this regime. Now, this root, although mathematically allowed, is a bit problematic in terms of physical interpretation, because it corresponds to u greater than 1. And how do we satisfy that with a real angle? We can't. So these are the 2 physical roots, or physically acceptable roots. And we can see this also from the fact that f is equal to the square of u derived. This has to be a positive quantity as long as u dot is real. If it's imaginary, it can become negative, but that would correspond to some purely mathematical allowed solution. And so due to this condition, we then know that the angle theta has to take values, it can only take values in fact, such that u lies in this regime, between the two roots here, such that the function is positive. So that's a pretty major step in terms of identifying how the top will move, because we've now identified the range of values that this angle theta can take. And as a way of visualizing how the resulting motion of the top will look like, imagine that this top of the top has some color to it, so that it can draw a line where the top moves. And what you will find is that the top moves such that you get a line along this unit sphere. So we're considering now the stationary system, and the top will move with theta. And from this analysis, we know that the values that theta can take are restricted to being between theta 1 and theta 2, corresponding to u1 and u2. So I don't know if you can visualize this, but the angles of theta should then be restricted between these two lines on a unit sphere. Can you see that? Yeah. So it means that the angle has to can only take values between here and here, which corresponds just to a given regime, namely here. Now, we've identified the allowed regime for theta, but inside this regime, different things can happen depending on the parameters in the problem, such as energy and mass, etc. These parameters alpha and beta that we introduced. So one possibility is that you have this kind of precession like this. So it's precession with the notation. What this means is that the top is precessing around the z prime axis. But it does so with a phenomenon known as nutation, meaning that as it rotates, it sort of bobs back and forth like this. If you've ever seen a top spinning on a table, you will actually see this phenomenon that it's actually bobbing while it's spinning. So this is called nutation. You can have other exotic patterns. You can have precession with loops. So the top is actually making loops as it's spinning. Yeah, I think we'll settle for those two. So the point is just that accompanied with the precession of the top as it's rotating around the z prime axis, you can also have an additional motion due to the way the top changes between these two extremal values. In order to derive precisely these patterns and see how they emerge, we would have to solve explicitly for theta as a function of time. And from the equation we had, that would be a pretty hard task. We could do this numerically, and then we would see something like this. Now, one might ask, is it possible to obtain a pattern with truly regular precession, so that the only movement of the top is that it's spinning without doing anything in addition to that, like notation or loops? So a regular precession would correspond to a case where theta is a constant. The top is just rotating. So it would mean that the allowed regime for theta is just one single value. So the question is then, what kind of condition would we require for the function f of u? So we had this equation telling us how u evolves with time, and in fact how theta evolves with time. So we see that if theta is supposed to be a constant, well then u dot should be a constant. So f of u has to be equal to 0, but it should only be allowed to be 0 for one particular value of theta. So we know that the function f behaves like this. It goes in minus infinity here and infinity here. And at minus 1 and 1, it has negative values. So the question is now, what has to happen for this to be fulfilled? Any ideas? So we're looking for a solution of this equation for one single value of theta.
Well, if it goes up to the f of u equals 0 and then down again.
Exactly. So something like this. Yeah. So the regular precession case actually corresponds to a scenario where the function f only has two roots. In fact, it has a double root here. We still have our unphysical solution for u greater than 1, but we also have a double root here. And since f of u, the physically allowed values of f of u are only greater than or equal to 0, this is the only possible value for theta. So something like this.